So as we talked about in class, valence bond theory can be contrasted with molecular orbital theory. Valence bond theory is much simpler. It's very advantageous when we have a large number of atoms. We can deal with large numbers of atoms quite easily, quite simply. And the reason we can do this is because the assumption holds that the atomic orbitals that we're dealing with and the hybrids that can be generated are pretty similar for each of the atoms. And so we can generalize. We can look at even the largest molecule as simple components. So even for very large structures, we can look at the individual atoms and tease out information regarding the behavior around the atoms, because we can look at each individual atom as a unit. And we can look at this carbon and see that it is sp3 hybridized, and that tells us the arrangement of the electrons, that this nitrogen is sp3 hybridized. And it has a lone pair on it, and that this carbon is sp2 hybridized. And so we can use this sort of to start to gauge and build structural information using this valence bond theory. Contrast that with molecular orbital theory. Molecular orbital theory is very also quite useful, but it has the advantage of it's actually a little more accurate description of what's going on at the and the difference between valence bond theory assumes that the individual atoms pretty much stay the same. Molecular orbital theory works under the assumption that the atoms are, all of the electrons are distributed across the entire molecule. So all the electrons are shared. Now, the sharing isn't always even, like we see with the valence bond theory. There are some elements that hoard the lion's share of electrons, or you could say the electrons reside more readily on those. And like valence bond theory, when you combine orbitals, okay, the number of orbitals in will equal the number out. So what I mean by that is if you combine two orbitals, two atomic orbitals, you get out two molecular orbitals. So let's take a quick look at the simplest case, is with something like hydrogen. And this is the example we used in class. Hydrogen has a 1s orbital. Each hydrogen has an individual 1s orbital. And in that is one electron. And when you bring those things together, they combine one of two ways. So the two orbitals combine, you get one low energy orbital and one high energy. And again, these are the individual atoms. And so what we really, these are the individual atoms. And they combine together to form a new set of molecular orbitals. And those molecular orbitals, there are two distinct molecular orbitals that form. There's the sigma orbital and the sigma star. And we would label this one a 1s because it's composed of a 1s orbital. So it's sigma 1s and sigma star. And the difference between this is one of these is a bonding orbital and one is an anti-bonding orbital. And that's common what we see. One bonding, one anti-bonding. So you bring in two orbitals, they form a positive interference and a destructive interference. What do these look like? This graphic shows you a quick picture. You see that you bring the two atoms together. At these 2 points is roughly where the actual atom exists. You have a constructive interference and you have a destructive interference. A slightly better picture would show this one, where you bring the two atoms together, and in one case their probabilities merge. And in another case, when you have the antibonding orbitals, you bring them together and they do not merge. You end up with opposite phases. And so you have one case where there's a buildup of electron density between, and that's usually where we have the bonding orbitals. It's usually buildup of electron density between the atoms. And so we have a buildup between the atoms, and here we have a usually node formation between atoms. Now these are denoted as being sigma orbitals because when we find the bulk of the electron density that builds up takes place directly within the bonding plane. So we're bringing these two atoms together like this, and we see a buildup of electron density between them. There's another type where we still see buildup of electron density, but it's not within the bonding plane. It's above and below the bonding plane, and we'll talk about that in a second. So that's the simplest, and so we can then take these two electrons and then populate, and again, this is Aufbau principle all over again. We can then populate these, and we find that the electrons now reside in primarily in the bonding orbital. And so we can talk about the molecular orbital picture, and we've got the sigma 1s and the sigma star 1s that arise from the 1s orbitals on these hydrogens, and we have this populated. So we can talk about the bond order, or the arrangement, and the bond order is the number of bonding electrons minus the number of antibonding electrons divided by 2 will equal the bond order, which is equivalent to, this will tell us information. Bond order is related to distance, as in the greater the bond order, the shorter the distance. The bond order is related to the number of bonds. And so we can change the bond order and start to see increases or decreases in the number of bonds. So, now, one of the things that we can't do with valence bond theory is look at unpaired electrons. So we can look at things like H2 plus, and we can then draw a molecular orbital diagram for H2 plus. Again, the 1s orbitals on the atoms interact to generate a high energy. And again, this overlap and combination of molecular orbitals usually takes place between orbitals of similar energy. Mostly what we're going to be working with will be identical molecules. I'll show you one that's not identical in this, maybe. So in this case, they only have, it's H2 plus. There is only one electron. That one electron ends up in the sigma 1s, and there's an empty sigma star 1s, an empty antibonding orbital. And so we can then say that the bond order for this compound is equal to 1/2. And so we could say that there's half bond between the hydrogen in those cases. That's molecular orbital theory at its simplest. Let's take a look at a slightly more complex case. Take a look at an oxygen molecule or something along those lines. And here we have an oxygen molecule. Again, if we're just going to, you can you can simplify this procedure by just looking at the valence shell. And the computer is freezing. All right. Looking at just the valence shell, and what we find is that we can combine the two s orbitals. And notice how the 2s and the 2p are not overlapping or not combining. The s atomic orbitals only interact with the s atomic orbitals. This isn't always the case, but in this case, because they're similar in energy, they form the best overlap to form these two the sigma. This would probably be the sigma 2s and the sigma star 2s, bonding and anti-bonding. And then we also talked about sigma and sigma star in terms of what happens when we have p orbitals interacting. When you combine orbitals, when you combine p orbitals again have this lobal shape with this node between them. You can combine the p orbitals one of two ways, and-on. And when you combine them like this, and-on, you get, in the bonding case, you get favorable overlap between the two. This again represents the atoms. So buildup of electron density between the atoms within the bonding plane. So this would be a sigma orbital, sigma 2p, and you can, and where again where that 2 denotes the primary quantum number. Or you can get a cancellation where you get a node that shows up between the atoms. And this would be the sigma star, the anti-bonding orbital. Now you can also envision another way of combining these, and that is not end-on but side-on. You can bring these two pi orbitals, these two together in a, you can combine them, and again you can combine them one of two ways. One that creates sort of an overlap of electron density between the atoms. This is what we call a pi bonding orbital. Notice there is a nodal plane that separates these two, but the buildup of electron density is still between the two atoms. And then there's also an anti-bonding orbital that can also result. So those would be the pi star anti-bonding orbital. Now, when we do this for something like chlorine, so you can actually look at these pi orbitals, and you see when they come together, they form this. This is a pi star anti-bonding orbital versus the pi orbital diagram. And you can see they form these kind of banana bonds that go above and below the plane of the bonding. But they're still bonding orbitals. So this is, again, just a better look at the diagram I showed. The anti-bonding are very similar. Okay. Again, two of these, one set of the p electrons forms a bonding orbital. A sigma bonding orbital. When we do this for something like chlorine, one set of p orbitals forms a sigma bonding orbital and a sigma anti-bonding, but the other two electrons are unchanged. Other two orbitals are unchanged, and they are degenerate. They have the same overall energy, and they combine to form new orbitals. And there's a slight energy difference, and there's only one way. There's only way. You just have to memorize it like this. Now, what that means is that you can then populate these, and you can start to see different behaviors. We start to fill this, and with electrons, and we can then start to look at the bond order. So again, this is the oxygen example, and we have 14 electrons in the valence shell, and they fill via the off-bow principle, and we get this Hund's rule behavior where the electrons sort of have to be paired, unpaired as long as they have to, and so this explains why oxygen is an unpaired system. Now, if you were to add electrons to this, you could add those electrons, and when you add those electrons, they would end up populating this pi star orbital. So when you form the -2 ion for oxygen, it would actually weaken the bond. But that's not always the case. Electrons going into an anti-bonding orbital will weaken the bond. Electrons going into a bonding orbital will strengthen the bond, and vice versa. So that will explain some of them. That's what you use to rationalize bond length changes when you change the number of electrons. That's again something you can't do readily with valence bond theory, which is why molecular orbital theory is much preferred. The difficulty is that once it gets beyond 2 or 3 atoms, it can get quite complex. So for instance, we can take a look at some molecular orbital diagram for something like HF. What we see is that some of the orbitals combine favorably and some of them don't. We have a sigma and a sigma star that forms from the 1s orbital and the 2p orbital. Again, very much like our valence bonding model, where the 2p has the unpaired electron and the 1s has the unpaired electron, and those are the ones that interact. Then you also have these other grouped atoms, and this and so we can use this to rationalize the structure of HF. So for multiple systems, we can actually start to see. So here is a molecular orbital diagram for something like water. Notice it is a bit more complex than our other examples, but some of the same aspects. On the left we have one atom, on the right we have the other atom, and we start to form orbitals of various characters. And they don't look the same as our simple examples, and this is why we don't often discuss them. But you can start to get a feel for the behavior between the atoms. And so let's take a look at along this oxygen-hydrogen bond. You can start to see that this would represent a bonding orbital between the oxygen and the hydrogen. And again, the same thing here. And then we can see some sort of another type of bonding orbital between the oxygen and the hydrogens here. Okay? Now, one of the things I didn't specifically mention in class was the presence of what we call the highest occupied molecular orbital, or the HOMO for short, H-O-M-O. Right? The H-O-M-O, the HOMO, is the highest occupied molecular orbital, and it's important because when we excite electrons, usually those are the electrons that are the most easily excited. They're the highest energy to begin with. And so they jump from the highest occupied molecular orbital to the next molecular orbital, which is the lowest unoccupied molecular orbital, or the LUMO. And so you will hear people talking about the HOMO and the LUMO, and what they're really talking about, or the HOMO-LUMO gap, that separation, energy separation between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And this is important in terms of electronic transitions within the molecule. They're not always bonding and anti-bonding, or notice how none of these have those descriptors that we discussed. Right? They have, but they do have relationships that deal with the symmetry of the orbital, how symmetrical they are. So that's molecular orbital theory in a nutshell.